In enterprise AI, the assumption that adding more data sources automatically improves a record is dangerous. In practice, piping in extra APIs, or application programming interfaces, very often destroys the underlying integrity of the system. Enterprise data streams are massive and messy, ranging from raw email threads to fragmented calendar invites. No single provider can capture the full context, so we have to enrich the data to make it useful. To fill the gaps, developers typically call multiple data APIs in a sequence, stacking responses on top of each other. At the code level, this relies on a dictionary merge, a programming operation where one set of key-value pairs is added to another. The code takes payload version 1 and runs an update function with payload version 2. This creates a blind, last-write-wins architecture. The system accepts whatever data arrived most recently, never evaluating which API actually provided the truth. Feeding probabilistic models and best-guess APIs into a naive merge function creates a cascade of errors that destroy system integrity. This failure happens quietly. Imagine an extraction pipeline successfully scrapes a highly accurate city location from a company website. You now have a verified fact. Next, the pipeline makes a second API call to a different provider, intended only to find a missing phone number for that same record. But this second provider returns a full payload. It includes the phone number, but also a low-confidence guess at the city, inferred purely from the phone's area code. The developer wants the phone number, but the system is programmed to process the incoming payload in its entirety. As the merge executes, the low-quality area code guess overwrites the high-quality scraped fact. This failure throws no errors. The record looks superficially complete, but the most accurate data has been erased. Deterministic workflows require structural defenses, or they will be destroyed by probabilistic API guesses. To protect the data, we implement a fixed-tier enrichment cascade. We route data through a specific sequence of 6 APIs, ranging from high-cost web scrapes down to basic area code approximations. We assign a strict numeric priority to every source in the pipeline. By bypassing an API's self-reported confidence scores, which are often just probabilistic guesses, we enforce a hard-coded hierarchy, 5 down to 0. Allowing ties between APIs creates ambiguous conflict resolution. A strict vertical order ensures the system never has to guess which source wins. This hard-coded hierarchy forces probabilistic data into a predictable, manageable operational structure. Supporting this cascade requires a change to the underlying database schema. Tracking data provenance at the record level is an operational lie. Real-world enrichment is always a patchwork. A standard database table that simply stamps an updated at time on an entire row cannot represent where individual facts came from. We solve this with per-field provenance. Every raw data field is paired with adjacent metadata columns that track the source of that specific value. This schema treats every data point as an independent asset, with its own explicit paper trail. These columns interface directly with our priority rules. The system now knows exactly which API provided which specific value. Enterprise records are built from fragments. Only field-level tracking reflects the reality of how they are constructed. Conceptually, this entire process runs like a high-speed relay race, where each runner is strictly permitted to only carry the baton forward. The first rule is that lower-tier sources are permitted to fill in empty blanks. The second rule is that a source may never overwrite a field already populated by a higher priority source. When Tier 5, our web scrape, executes, it might find the company name but leave the city field blank. Later, Tier 1, Azure Maps, accurately fills that blank and stamps its identity in the provenance column. Finally, Tier 0 generates a guessed city based on the phone number and initiates an overwrite attempt. The system checks the provenance column and identifies the existing Tier 1 tag. Because 0 is lower than 1, the system rejects the overwrite, protecting the higher quality data. Deterministic merge logic is the only way to actively protect high-quality facts from low-quality inferences. This hierarchy also provides operational resilience when managing API costs. Fallback systems that lack predefined priority rules are brittle. If a primary tier goes down, the remaining sources often overwrite each other randomly. The Cascade architecture solves this by interacting with environment feature flags. If we need to save costs, we flip a toggle and Tier 5, our most expensive API, is disabled. By disabling the top tier, Tier 4 dynamically promotes to the authoritative top position of the stack. The same merge rules apply. The system simply bypasses the disabled tier and executes the standard priority logic through the remaining active sources. Decoupling these cost decisions from strict data integrity rules ensures highly stable, predictable performance in a live enterprise production environment. All of this back-end engineering is designed to deliver a single, dependable truth to the human operator. To the user, the record simply looks clean and fully populated, but an X-ray mode reveals the underlying provenance tags attached to every field. Human reviewers use these tags to audit the system, identifying exactly which API provided a specific spelling or an unexpected phone number. This transparency builds trust. Operators see immediately if a city was scraped from a website or approximated from a phone number. We replaced the gamble of a blind dictionary merge with the deterministic accumulation of facts. The system can now prove whether a data point was scraped, searched, map-grounded, or simply inferred. Engineering for reliability means building the rigid, unglamorous rules that force probabilistic models to behave honestly in production,